Hi, here we are discuss about the efficient CRC-BCH unified encoder for global positioning system. Here, the proposed approach of this work, we have developed the FPGA implementations of CRC-Enhanced BCH and Hamming code for fault-tolerant parallel filter architectures in GPS and space application. Here, this project introduced a novel fault-tolerant parallel filter architectures that integrate a cyclic redundancy check and BCH and Hamming error corrections code to improve the fault detections and corrections in GPS and space applications. By embedding CRC with both encoders and decoders, this designs enhance the traditional error corrections mechanisms, allowing for more efficient handling of robust error detections, particularly for burst errors and complex error patterns commonly found in a space environment. The CRC-enhanced architectures ensures a higher reliability and data integrity, addressing the limitations of traditional error corrections method. Here, the CRC-BCH combinations addresses multiple bit errors, while the CRC Hamming combinations corrects a single bit errors. So, ensuring this higher data integrity under hash environmental conditions by embedding CRC within both the encoders and decoder architectures provides a lightweight and power efficient solutions, reducing the risk of undetected errors, especially when the primary ECC reaches its corrections limit. A fault injection simulator is employed to test the robustness of the designs by introducing random fault. The architecture is implemented in Verilog HDLs and synthesized on RTX 7 FPGA using VADO software. So with the key performance metrics like area, power and delay and error corrections efficiencies evaluated for space communications and data processing system. Now we can verify the paper. So this paper is fully designed for the CRC error corrections method, which using the fault tolerant method of BCH and Hamming code for space applications. Okay, so this method we have used some reference papers. This is one of the reference paper from 2024. So here they are developed the CRC BCH method with a combinational logic. Okay, but we have implemented this logics in a parallel filter format. For that proposed architectures, we have choose this paper, the fault tolerant parallel filter based on error corrections code. Okay, so here the Hamming method, it will be designed using the fault tolerant parallel filter architectures. Okay, and the BCH code for multiple error corrections, they have developed a multi-bit error corrections code which using this architectures in figure 3. Okay, for this Hamming and BCH code we need to test with a simulator. For that reasons we have used this method to improving error corrections code for multiple cell upset and space applications. Okay, so here the figure 10 it will be shown as a block diagram of fault injection simulators for ECC corrections method. So here we have added CRC. Okay, and it will be support for additional error corrections to avoid mismatching data in the decoders. The primary focus of this project is to develop an efficient CRC enhanced ECC architectures capable of addressing the unique challenges posted by SCU and MCU in GPS and space applications. For additional proposed, we have used this work, so a decoder for short BCH code with a high decoding efficiency and low power emerging memories. Okay, so using this architectures we have developed the Hamming and BCH code using this architecture of single error corrections and multiple fault error corrections with support of this flowchart. Figure 5 conceptual block diagram of DCT-BCH decoder. Okay, so here as per the architectures we have used for single error corrections and double error corrections and non-error corrections method we have integrated with this project. Okay, so both Hamming and BCH code we have generated as per this architecture. Okay, with support of the fault tolerant. Okay, now we can verify the Verilog HDL coding part. Okay, so here this is a Hamming code. Okay, so here this is a test bench of the code. Here we are checking the CRC pass or fail in ASCII. Okay, and we have generating the input, and this is the top model of the code. Top model of the code will working as a fault injection simulator. Okay, so here the Hamming encoders and Hamming decoders and comparators and XOR gate available as per the injector rules. Okay, so inside of the Hamming part we have added with the CRC protected, and the Hamming decoders we have used for CRC generator to verify the CRC in the Hamming decoder. Okay, and it will be provide the CRC status. Okay, so this status we have used with the CRC pass or fail. Okay, and this is a code for BCH. Okay, so this is also same, but the bit size of the BCH for multiple bit error corrections we have used 49 bits. Okay, and the Hamming will be used for 16 bits. Okay, 16-bit input and 16-bit output. Okay, then BCH is a 49-bit. Okay, so as per the same method we have generated the multiple error corrections in BCH format with the same fault injection simulators. Okay, and this simulation part we have done with an modelism. Here it's a simulation results. Okay, so here you can verify the X input error. For error we are using a multiplexers. If you are given a error equal to 0000, the error will be not generated. So in case we will be given a 1111, the error will be generated. At that time the Hamming code will be correct the error and it will be provide the original results. Okay, so here I can verify the YX output. It's the output of the Hamming code, and X is the input of the Hamming code. Okay, and here this area the error will be generated. Okay, generally the Hamming code will not predict and correct the errors at 100% accuracy. It may be it will be create error losses also. Okay, so that mismatch we need to protect with the CRC. Okay, so here our CRC it will be protect, it will be showing the CRC fail. Okay, so you can analyze the RW. Okay, so it's also it will be showing zeros only. At the time of the error that will be goes high. Okay, so you can analyze the data completely. Okay, CRC pass. Okay, so we can analyze and run all. Okay, so all the data comes with CRC pass. Okay, and the BCH simulations it will be goes the same method, but the bit size it will be different. Okay, so here you can analyze the data input RW and CRC status CRC equal to pass. Okay, so here also you can analyze the n times. Okay, so here it will be correcting the data and it will be showing the output, the YX. Okay, and this code we have synthesized in Vado using a ATIC 7 FPGA. Okay, so here this is a code for Hamming. Okay, Hamming synthesized report. Okay, so in the project summary you can analyze LUT and IOB and power consumptions. Okay, and you can analyze a schematic. Okay, so in the schematic you can analyze a clear view about the architectures. Okay, how we have designed this code. Okay, so here the X input, so the X input given to the comparator as well as a Hamming encoder. So inside of the Hamming encoders we have used for code encryptions and the Hamming code architecture as per the same in a parallel filter. Okay, and additionally we have added a parallel CRC 16-bit architecture. Okay, so this is CRC 16-bit architecture. Okay, for parallel. Okay, and this is a Hamming code. So instead of the Hamming code the architectures will be present here. Okay, so this is a XOR gate, it will be adding the error. Okay, so once you enter the error it will be XOR into the original value and it will be produce the final output with the error. Okay, and this is a Hamming decoder. So this decoders it will be have this method of architectures. Okay, so this flowchart of architectures. Okay, so the encoder part will be used with this architectures with support of the parallel filter, and decoder part we have used this part of architectures. Okay, syndrome generators, error counters, double error correction, single error corrections, and no error. Okay, so here, so this is the final architecture of the decoder part. Okay, and as per that, here you can analyze the symptom generator and the XOR counter and double error correction method and single error correction method and multiplexer and error correction, okay, and the parallel CRC 16-bit. okay. So here the CRC, predicted CRC, it will become as an additional input, okay. So here the parallel CRC, it will be generate the CRC for decoding purpose, okay. So the decoder final output we have used and we will be generated the CRC here, okay. Finally we will be matching this CRC, predicted CRC and generated CRC using for CRC checking, and we will produce a CRC status here, okay. So that status will be converted to the ASCII. In simulations it will be showing for CRC pass or CRC fail, okay. So here this is a 16-bit CRC, same code, okay. Here this is a BCH synthesis report, okay. Here you can analyze the BCH data analysis using the post implementations. It will be take 915 and 78 and 118 and 1, and here it will be take the delay part equal to 4.315, hold and pulse width modulations, and here you can analyze the power consumption, okay. So here this is a schematic for BCH, okay. So here you can analyze the BCH encoders and XOR and BCH decoders as per the fault injection simulators, okay. So inside of this BCH encoders, this is a multiple fault error corrections encoder, okay. So the code encryptions with the BCH codes, okay, and here we have added a parallel CRC 49-bit. This is a parallel CRC RTL schematic, and this output we are given to the XOR gate, okay. So it will be adding the error here, okay. After that we are given this data to the BCH decoders, okay. So here it will be same as a symptom generators, error counters and double error correction, single error correction method, and the multiplexers finally come up with the error corrections. So this error correction output given to the parallel CRC 49-bit, and it will be generated CRC, and predicted CRC we need to verify it with using a CRC checking, and finally we are given the CRC status, it's a pass or fail, okay. So here we have compared this analysis using a comparisons table, okay. So this comparison we can put the both encoders, decoders and CRC for Hamming and BCH, okay. So we can possible to draw the table using separate method also, encoders also and decoders, okay. So here so this is a comparisons analysis chart, okay, and we have written abstract document for this project. This is a title, proposed abstract, improvement of the project, proposed systems, okay, and problem statement, contributions, and the detailed notes of this project, okay, with a literature survey and the references, okay. Thank you.